And we're going to talk here about collisions and the three types of collisions that you're responsible to understand for the AP exam. In order to analyze all collisions, we have to make an assumption, and it's this. During any collision, the amount of time that passes while two objects collide is 0. It is a negligibly small amount of time. The reason that's an important assumption is because it allows us to say momentum is always conserved in all collisions. Now, there are exceptions. If a problem, for instance, tells you the amount of time that passes during a collision, well, then obviously you can't assume that it's 0. You have to account for that. But unless it says that, we will make the assumption that momentum is conserved. And the reason that the negligibility of time causes momentum to be conserved is because external forces, which would otherwise accelerate the system, don't have any time to accelerate the system. If no time passes, a non-zero force won't do anything. It's too quick to change the momentum of the system. So imagine that you had two skydivers, and the skydiver that's higher up, farther from the Earth, is moving a little bit faster. And the goal is to make a formation, and they're going to hold on to each other and then fall as one. When that happens, they're just so not the same two skydivers, but it's hard to find images on Google Images that match up perfectly to what I want to say. Anyway, so once they latch onto each other and they move with a singular velocity, I think it should be obvious that they do not exist in an isolated system, right? They are falling through the air, which means that there is an unbalanced external force of gravity. Well, so if your system's not isolated, your intuition should be, well, then they won't have conserved momenta. But they do, only for that brief instant when they are colliding. All right, so there's three different types of collisions. Here they are. Let's talk about what they have in common and what's different. Elastic collisions are collisions in which two or more objects, but usually two, bounce off of each other without losing any energy. Because there is no energy loss to friction or air resistance, there are three conserved quantities. One is kinetic energy, two is relative speed, and three is momentum, like all collisions. I also want to make special note that I consciously used the word speed here rather than velocity. So the relative velocity between the objects is not conserved, but the speed is. And we'll do an example in a moment to explain the difference and what that means. Inelastic collisions are ones in which the two objects bounce off of each other, again, same as elastic, but they do lose energy in the process to heat and friction and things like that. Therefore, the only thing conserved is momentum, and completely inelastic collisions are ones in which objects collide and then stick together and move with a singular velocity like the skydivers on the preceding slide, and only momentum is conserved. You have an empty train car, not pictured, and it's moving with 20 meters per second of velocity, and its mass is 25,000 kilograms. We're going to then drop 75,000 kilograms of coal, and that is what I've shown in the image here, and we want to figure out how fast will the car-coal system be moving after the coal has been deposited in the car. I'm going to let you pause the video here and see if you can determine the final velocity of the coal car system. We're going to show the solution now. So the first thing to consider here is what will be conserved. Well, like we said a moment ago, completely inelastic means only momentum. So I'm going to use momentum conservation. Momentum of the car plus the momentum of the coal is equal to the momentum of the car plus coal, and I've only combined them on the right side here because they're going to move with the same velocity. They've joined together. That's what a completely inelastic collision is. So you can write this as P prime car plus P prime coal. That's fine, but it's the same velocity, and so that's why it's one term for me. Also, one other note, I didn't actually say it anywhere explicitly, but it's very important to remember that momentum is a vector quantity, and therefore you can only analyze it in one dimension at a time. So everything I've written here is the x dimension only. For instance, if I go to expand this to mass times velocity for each term, I'm going to plug in a velocity of 0 for the coal. And that should make sense if you remember that we're in the x dimension, because the coal was moving, right? It was moving vertically downwards. It was dropped from above into the train car, but its velocity horizontally was 0. So that's why it's important to keep your dimensions separate. Also, one last note, this is, again, why I've chosen to combine everything on the right side of the conservation analysis, is because you can just say the mass of the car times the v prime of the car plus the mass of the coal times v prime of the coal. But since they have the same final velocity, v prime, you can just factor it out and then put the masses together in the parentheses and sum them. Okay, so 25,000 times 20 plus 0 equals 100,000 v prime. Solve it and you get 5 meters per second. Conserved in all collisions is momentum, and then because this is elastic, we know the kinetic energy is still conserved, and we know that the relative speed is conserved. And I want to look at the relative speed idea in this question because it's not maybe as obvious as what I mean when I say that kinetic energy is conserved. Also, one final note, I don't say it in here anywhere, but it's a frictionless surface. So, I mean, you should be able to get that from the elastic collision. You wouldn't have an elastic collision if there was friction, but whatever, just to be explicit. So these two kids are going to ride their sleds, and they're going to collide and then bounce off each other without losing any energy. That's what elastic means. Also, I'm going to take each child and the sled that they're on to be the system. So this is a 40 kilogram system moving at 8 meters per second. And then here on the right side, we've got a 80 kilogram system, sled plus child, moving to the left at 2 meters per second. Feel free to do so. I am going to go through the solution though. So here we are. Starting from momentum conservation, which is a great place to start every single time with collisions, because it's the only thing that will always be conserved. I'll say that the initial momentum of child A, which for me is the child on the left, plus the initial momentum of child B is equal to the sum of their final momenta. Notice I did not combine these into a single term like on the car, coal, train question. The reason is that they're bouncing off each other and then moving with two different speeds. They don't combine together and move as one, so you can't just say the mass of each child combined times their joint final velocity. So let's plug in some known values here. MAVA plus MBVB. I'm just replacing P's here with what the P formula is. Momentum is mass times velocity. And the known values are the 40 kilogram mass times the 8 meters per second for child A, and then 80 kilograms. And notice you have to use a negative sign. This is a really, really important point because you get a completely different answer if you don't. If you put in a positive 2 and a positive 8, that would mean they're moving in the same direction. But because they're moving in opposite directions, one of these two numbers, either the 8 or the 2, has to be negative. Doesn't matter which one. And then that equals the sum of their final momenta, math, 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 algebra, algebra, and we're left with two unknowns. So we appear to be at an impasse, and that is why elastic collisions are so useful, because three things are conserved. You have up to 3 equations to use to solve for multiple unknowns. So let's see if we can't make use of one of the other conserved quantities. We have both relative speed and kinetic energy. We already solved for the momentum. This is the equation from the last slide, so I just want to have it so we can see it. Well, like I said, we could do it either way. We could do this with relative speed, or we could do this with kinetic energy conservation. I'm just going to do relative speed because it's something we've never seen before, and it's really important that you know what I mean by speed rather than velocity. They do not have a relative velocity that is conserved. So how do you say that the relative speed between two things is conserved? Well, first, the relative speed just means the difference in their speeds. How fast is one moving with respect to the other? And so I'll just subtract their initial velocities. Their final relative velocity here will be the final velocity of A minus the final velocity of B. Here's why this doesn't say velocity is conserved. It says speed is conserved. The subscripts change. B minus A equals A minus B. So what does that mean? It means that the magnitude of their velocity is conserved relative to each other. In other words, if two things are getting closer together at 10 meters per second, after they collide, they will be moving apart at 10 meters per second for elastic collisions only. And that is the number in this case, so that's why I chose it. -2 again, because the child on the right is moving to the left, and that's our negative direction. So the relative speed, B minus A, -2 minus 8 gives a -10. So the difference between their initial velocities is a -10. Therefore, the difference between their final velocities will be +10. So speed, or the magnitude of velocity, is conserved, but not velocity, because that has to be specified with a direction. Direction changes. So you could solve this one of two different ways. You could either solve this for v prime a or v prime b. It doesn't matter which one you choose to do. But either way you go, you're going to take the expression for either v prime a or b and plug it back into your momentum conservation equation for the expression you solved for, and then you've eliminated one of the two unknowns, allowing you to solve. The two equations I just showed on the last slide side by side so we can refer to them easily: momentum conservation and then relative speed conservation. I've just chosen to solve arbitrarily for v prime a, but again, you can do it either way, it doesn't matter. So what am I going to do? I'm going to take this expression for v prime a, v prime b minus 10, I'm going to plug that in for v prime a here in my momentum conservation. And just to make it clear what I'm doing, whenever I show math in these PowerPoints, I'm going to use brackets whenever I replace something with an expression from another equation. So here v prime a was replaced by v prime b minus 10, and that's why I put it in brackets. Now we have to distribute that 40 to both v prime b and to negative 10, giving us 40 v prime b minus 400 plus 80 v prime b. And we have some common terms here. We can combine these to be 120 v prime b. Then we can add the positive 400 to both sides, so it'll be eliminated on the right side, negative 400 plus 400, and the left side becomes 560. Divide both sides by 120, and you get your final velocity of the child that was initially moving to the left, and note that his final velocity is positive. Literally, that means that we move to the right. We have a physical significance to the sign of the answer. That also allows us to now finish this. So if we know the velocity of one child, how can we get the velocity of the other child after the collision? That means we're just going to plug it in. V prime b is positive 4 2/3. Sub that here. Again, brackets, because I brought this in from another equation. Subtract the 10. That was part of the relative speed conservation equation. And your final velocity of child A is negative 5.33 meters per second. How do you know if you're right? There is a super fast check to this. Well, we know that before they collided, they were getting closer together at 10 meters per second. The negative sign here just meant towards each other. That means if we did the math right, then after they collide and bounce off each other, they should be getting farther apart at the same speed. So child B will now be moving to the right at 4 2/3 meters per second, whereas child A is now moving to the left at 5.33 meters per second. They are getting further apart at 10 meters per second. We did this correctly.